This little presentation is about hybridization. We're still on molecular structure, so we're still getting the introductions. Now, you may or may not have done hybridization in Gen Chem, it depends. So if you have not, this is great. If you have, you can, speed my voice up if you want to. No problem. Okay, so in case of bonding, which is our main thing that we're talking about in the first chapter, is, different kinds of bonding that we have. Ionic we will not cover because, carbon compounds don't really have that much of ionic bonding. So we're talking about covalent bonding. So in covalent bonding, the one theory that you know about is the Lewis theory, right? We talk about this all the time, is that the Lewis theory is when you show the valence electrons bonding and you show the electrons as dot structures. So it's a very innovative theory when it came out, and it still works fantastic. We use a Lewis theory all the time, but it still has its problems, okay? Or I shouldn't say problems, it has shortcomings, okay? In the sense it doesn't explain everything. So it explains everything as in how bonding occurs and the number of bonds and the octet rule. Everything is fantastic, okay? But what it does not explain sometimes is the kind of orbitals we have, okay, and how the overlap occurs with those orbitals, because we actually have SPDF orbitals. And what are these orbitals again? These are spaces where electrons exist, right? Mathematical spaces. So Lewis theory doesn't talk about those kind of orbitals at all. When we show the dots around any atom, we're just showing dots. We're not saying that this is an S electron or a P electron. The valence bond theory, which is also the hybridization theory, actually goes a little bit deeper, okay, into that and says, okay, you have these electrons which exist in these orbitals or which exist in these kind of shapes. So how do we show bonding for that? Okay, so which means that we have to take the orbitals into account. Okay, and remember that any one orbital will have only 2 electrons, right? So an orbital with one space will have, 2 electrons. So S has only one space orientation, 2 electrons. P has 3 orientations, so it has 2 times 3, 6 electrons, and so on. Okay, so there are, those kind of considerations. The other consideration is the shape of the molecule, the shape of the orbital. So S is pretty nice, right? S is spherical. So S has really, I wouldn't say any other has major issues. It's just that you have to understand how it works. And so S, which is a spherical orbital, has a different kind of an overlap than a p orbital would, okay, because a p orbital is a dumbbell shape. So a dumbbell shape, when you write that out, what are you going to overlap? Are you going to overlap this? Are you going to overlap this? Or are you going to overlap all of this? What are you going to do? A spherical shape is like this. So are you going to overlap just this much? Are you going to overlap this much? So generally, it is considered that for covalent bonding, the overlap should be maximum as much as possible, okay, in there. So we know that what I drew over here is completely wrong because this is a better overlap of s orbitals, okay. Now for p orbitals, it's not going to overlap on both orbitals, so we say that, okay, it'll overlap only on the one side, which is out, and that depends also whether it's P, X, Y, Z, which one is it. So that also is something we have to consider. I will not be getting too much into that, but you should know that that is also an issue, okay, when we get into valence bonding. So here I just want to explain how the Lewis theory is different than the valence bond theory, okay? So if you have Lewis theory and you're looking at a molecule like methane, which is a very simple molecule, right? So if you were writing the structure of methane, it would be something like this, right? That would be the Lewis structure, and yes, you have 100% points because that is the Lewis structure. Well, when we get into the valence bond theory, now we're getting a little bit deeper into it, and we'll say, okay, well, 2 electrons on the carbon are s electrons, whereas the 2 electrons on the carbon are p electrons. Why? Because the electron configuration is 2s2, 2p2 for carbon. For hydrogen is 1s1. So hydrogen, no issues, right? So you can see that in green, that hydrogen is all spherical, it's all fine because it has only one shape. But carbon actually has two shapes, okay? It's the S and the P. So this is what the bonding would look like for carbon if we were to draw the orbitals, which means it looks really weird, right? So it shows that these two bond lengths are different, the bond strength will be different, but we know after studying methane that this is not true, okay? That all the bond lengths are equal and all the bond strengths are equal. So which means there is something else going on, okay? And that something else that's going on is explained by hybridization. So what is hybridization? Hybridization is formed by mixing of orbitals. Okay, so it turns out that those S and P orbitals that we were looking at just now, those will be mixed up. Okay, so they will not remain as S anymore or P anymore. They will lose their character, individuality, and they will mix up into forming some new orbitals. Okay. Anything that I'm talking about right now, this has been studied. It has been also observed in instrumentation. So this is, it's a done deal. All right. There is done deal for now until we find something more. But until now, it's a done deal. Okay. That there is hybridization that occurs. And that hybridization, as we say for hybrid, it's a mixing of something. Okay. Once you hybridize something, okay, it is hard to unhybridize it. It's not a physical thing, it's a chemical thing. Okay, so when you do reactions, when you form new bonds, when you form new molecules, in there, then you have all of these reactions happening, energy changes happening. That's when all this hybridization takes place. Okay, so you can do another chemical change and you can unhybridize, but again, chemical change and energy, okay, will require that. So here are the different kind of hybridizations that are possible. So we have sp hybridization. Sp means you have one s and one p orbital. And since you are mixing two orbitals, you will end up getting two orbitals. sp2 is one s orbital and two p orbitals. So this 2 actually stands for the two p orbitals. So 1 plus 2, 3 orbitals. So you end up getting 3 sp2 orbitals. Okay, so whatever number of orbitals you're mixing, that's the number of hybrid orbitals you get. It's like taking, I don't know, a concentrate of orange juice, and adding 3 cups of water to it to make 4 cups of orange juice, right? So now you have 4. So 1 plus 3 to give you 4. That's how it is. So that's hybridization in there. So we have all these different kinds of hybridization. D would be when you have expanded shell. So you start mixing up the d orbitals. I would like to focus on the sp, sp2, sp3 because this is the maximum that carbon can have, which is 4 bonds. Okay, so we'll do these 3 hybridizations. So this explanation here is for you when you read the book, so you understand what I have done in the next slides. In the lecture, you don't need it because in the lecture I'm talking to you, right? So I will explain everything to you. But you may want to read this through when you're reading this on your own because you will see as the next 3 slides are very busy. Okay, there's too much going on. So I've given you the Lewis structure, I've shown you the configurations, and then I've shown you the new structures in there. So there's lots going on. So it's much better to kind of let me just go through the slide here with you, okay, for the next one, for the hybridization. So then when you read this, you will understand. So here is the busy slide. Okay, so here you can see there's lots of stuff going on. So 1, 2, 3, 4. Okay, as I've explained in my previous slide. Okay, so you can read that when you get time. But here I am telling you this. So we're dealing with sp3 first. Okay, so remember sp3 is 1s orbital and 3 p orbitals. Example we're going to take is methane. Methane looks like this. Methane has a formula for AX4. Okay, now I'll be dealing with AX formulas all the time. If you need help with AX formulas, come and see me or email me, or there's another lecture I have on AX formulas in Gen Chem. I will give you the link for that, okay, in there, so you can go to read that up. But AX formulas are your friends, okay, they're your very good friends in chemistry. So methane is AX4, A central atom, 4 atoms, okay, all around. All right, so now for this one, this is the electronic configurations that we're dealing with. So let me explain to you what we're doing here. This is the ground state for carbon. Now we're taking only the second shell because second shell is the valence shell. So I'm not even dealing with the core electrons, okay? So this is the valence electrons, 2s2, 2p2. This is the ground state. In the excited state, this is when bonding has to occur, electrons will jump to a higher level. So the electrons from S2, 2s2 will jump up here. So now you have 2s1 and 2p3. Now the red box here shows you what is mixing together. So you have 4 electrons mixing together. What 4 electrons? 1 of the s electrons and 3 of the p electrons are mixing together. So you have 4 orbitals mixing together to give you 4 orbitals, and that's sp3. Now these 4 orbitals have both the characteristics of the s orbital and the p orbital, but they're neither S nor P because this is something new, okay? And that something new looks like this, all right? So you have these new orbitals in there which look neither spherical nor dumbbell, okay? So this is a little bit different looking. Now, how do you see these orbitals? Now, different books will have different shapes for you, all right? So I also draw a little bit different shapes sometimes. So it depends. If you see it in a book, don't be confused, okay? So s orbital means that you have in sp3, it means you have 25% s character and 75% of p character. So which means that the dumbbell originally, which the p orbital is just like a dumbbell, is not going to be a dumbbell anymore because it has the s character in it too. So it's a little bit more circular now. Okay, so this one doesn't show the second orbital in there, but it will be a little bit more circular dumbbell shape. Okay, that's what a new orbital would look like. If you don't know the new shape, it's totally fine, but I need you to understand that it's neither S nor P. It's a mixture of both, okay, in there. Okay, so now we have sp3 orbitals. Now again, we have 4 orbitals. Those 4 orbitals are exactly the same as you can see over here. They have the same energy, unlike S and P, which were different energies. Now these sp3 4 electrons are exactly the same energy. They look exactly the same. So now when you form the bonds with hydrogen, this is hydrogen. Now when you form the bonds with hydrogen, all the bonds look alike. Okay, so now this makes perfect sense that, yeah, you know, all the bonds should be the same. For methane, it should not be different looking bonds, all right? So that is what we end up happening in there. So this one is coming from the hydrogen 1, this is 1s1, and this is the sp3 for carbon, okay? That's what these two electronic configurations are. Okay, so one last thing to mention before I go on, actually 2 last things to mention, okay, before I go on from here is number 1 is that the new bond that you're forming here is called a sigma bond. Okay, so a sigma bond is a hybridized bond. A sigma bond is also a single bond. Okay, as you can see, it's a single bond. Methane has single bonds, right? So a single bond, that's going to be a sigma bond. The other thing is that the AX formula is still AX4. That has not changed. All right, which means carbon was a tetrahedral before, carbon still is a tetrahedral. So as you can see, we've not changed anything about the properties of methane. The only thing we have changed is our understanding of the bonds, okay, in there. So now we have a better understanding of the bonds because now we can understand how we were able to have exactly the same bonds in there. Okay, because we are supposed to have the same bonds, all right? All 4 bonds should be exactly the same. So those are the things, okay? So the characteristics of an sp3, okay, you can write that down somewhere if you want to separately. sp3 characteristics, I have a separate slide also here for you, but sp3 hybridization is AX4 and all the things that go with AX4. Tetrahedral shape, right? So here it is a tetrahedral shape, 109-degree bond angle, all of that goes with any kind of tetrahedral or AX4. That's how it's going to be. So that has not changed. Okay, the only thing that has changed is that the 4 bonds are hybridized. This is sp3. Okay, there, I had that too in there. Okay, all right. So now let's go on to sp. Okay, now let's look at sp2. Again, it's the same kind of a layout, okay, so that you have some consistency. The example we are going to take here is BF3, boron trifluoride. So here is the Lewis structure for it. This is what the model would look like. It is trigonal planar. All bonds are equivalent in the sense that, you know, they're the same. And the formula is AX3, okay, for it, the Ax formula for it. By the way, in case you're wondering what the Ax formula is good for, it's good for everything, okay, for determining the electronic geometry, for the shape of the molecule, and for bond angles. It's really fantastic. Okay, so now let's look at boron. By the way, if I haven't mentioned it, let me mention it here. When we look at hybridization, we look at hybridization only for central atoms. Okay, so fluorine is not hybridized, boron is hybridized. So in sp3, carbon was hybridized. So the terminal atoms don't matter so much. Okay, so here we have boron. Here is the electronic configuration for boron: 3 electrons, 2s2, 2p1. This is the ground state. And now we have the excited state. So here in the red box is what we are mixing. Why are we mixing this? Because this one is empty. We don't need to mix this, okay? In the excited state, 1 electron jumped from the 2s to 2p1. So now we have the 2p electrons here, okay? So, and not the 2p, but I should say the p2, okay, which is the 2 electrons in the 2p orbitals. Yeah, too many 2's. Okay, so you mix these 3 electrons, 3 orbitals, and you get this new hybridized state, which is these 3 electrons. The fourth one is empty. So now there's a little bit of correction I can make here in case it's bothering you. It's bothering me obviously enough to mention this, but this is actually a p orbital, and that p orbital should be high up here because p is going to be a little bit higher in energy than the sp2, because sp2 has the energy of S and the P, so it lowers it down. That's why you can see that I've drawn it kind of in the middle of both of these. So the energy level is in the middle, okay? So the P orbital actually should be higher, and this is empty because there is no electron to put in there. Now, in this new hybridized state, okay, that we have for sp2, now the S character is 33% and the P character is about 66%. So as we were talking before, the new orbitals here, they haven't quite shown clearly as to what's going on, but it's a little bit going to be even more rounder because in sp3, the S character was 25%. Now the S character is 33, which means more spherical. Okay, and so the dumbbell becomes a little bit more spherical in nature. Okay, so here is the F orbital. Here is the B, new electrons. Okay, and the new orbitals that we have. And so now this is the new structure. So all the bonds look alike now. And again, all the bonds are sigma bonds, which are the hybridized bonds, single bonds. The F is the p orbital, and that's why you see that as a dumbbell. Okay, and this green that you're seeing here, that is part of the dumbbell for fluorine, okay, in there. So that's what it is. Now, what has not changed? The bond angle has not changed. The Ax formula has not changed. The shape has not changed. Trigonal planar 120, that remains the same. The only thing that has changed for us is our understanding of the bonding now. Okay, so we've gone from Lewis structure to now hybridized. Okay, so that is kind of what's happening here. It's give you a little bit more understanding of how the orbitals play a role. Now, SP should go a little bit faster for us now because I've gone through a lot of things here. So I'm going to go a little bit, you know, as I usually I speak fast anyway. All right, so here's beryllium chloride BeCl2. Here's the Lewis structure. Here is the model. It is AX2, that's the formula. So A and then X2, the 2 atoms. It's a linear structure. and both bonds are supposed to be equivalent. So here is beryllium, and if you're thinking, oh my God, beryllium is supposed to be group 2, well, it can have a little bit of non-metallic character. So here the S orbital here gets excited, moves up. So you have one p electron, one s electron in the excited state. Both of these are getting mixed up to give you the two new orbitals. And again, you can see that I drew it like this, but technically, again, let me go ahead and cross that out and put that up here, okay? Because the 2p should be up here. They're empty, okay? But they're there, okay? And then you have the new orbitals, which is now the s and the p. So sp hybridized, this is going to be a 50% character now, right, for s and also for p. So it's really, really pretty dumbbell. So what they are showing over here, by the way, I did get some of these pictures from another photos, because I don't have the software to draw all these things, but I'm drawing over here to show you that what they have shown is the hybridized, just a different color, okay? But the shape of the orbital will also change slightly to give you a little bit of a different look, okay? Because it's neither dumbbell, neither spherical. Okay, so now for beryllium chloride, so here is the chloride orbital, and then here is electronic configuration, and then here is the beryllium, and here is the bonding again. So again, it doesn't look very different. If you were to draw the structure out, it will still look like this, and you're like, whoopee-doo, it doesn't look any different. No, it doesn't, and that's not the point, okay? The point is not to make it look different. The point is to understand what these bonds are made up of, okay? And so these bonds are sigma bonds. As soon as you hear sigma bond, you're like, it's hybridized. Now, what kind of a hybridization is it? Now, in this case of BeCl2, it's going to be an AX2 hybridization. Okay, so that's kind of how it goes. Now, the properties remain the same, which is that it is still going to be linear, and the bond angle will still be 180. Okay, so those kind of properties have not changed. So we did sp3, sp2, and now we did sp. Okay, so how do you know the hybridization? What I explained to you with these three examples is hybridization. I explained to you from forward and going on to hybridization. What you will generally be doing is the opposite, which means that you will have a structure, and then you will look at that structure, and then you will determine the hybridization. Okay, so see, I mean, in mine, I had the structure, and then I was explaining to you how hybridization occurs. That's not what you will have to do. You will just have to look at a molecule and predict what kind of hybridization it will have. So how do you do that? Okay, you draw the Lewis structure. There's no life without Lewis structure. So draw the Lewis structure, write the Axe formula. Okay, again, I can help you with the Axe formulas if you have forgotten those. Then once you have the electronic geometry, then you can figure out the hybridization. Now, Axe formula gives you two things. It gives you the electronic geometry as well as the shape of the molecule. To know the hybridization, you need the electron geometry. Okay, what do we mean by electron geometry? So let me just explain to you just a tad about electron geometry. So if you have a formula, say AX2 E2, that's 4, okay, which means you have 4 electron pairs or 4 electron groups around A. If you have AX4, that is also 4 electron groups around A. But in AX4, you don't have any lone pair of electrons. In AX2E2, you have 2 electron pairs. The electron geometry is how many electronic groups you have around the central atom. So here, if you have AX4, both of them are going to have a tetrahedral electron geometry. Both of them are going to have 109-degree bond angle. What the shape is going to be is determined by the number of atoms connected. So in AX2E2, which is the Lewis structure for water, the Axe formula for water is this. So you have the 2 lone pair of electrons here. AX4 we just did, right, which was CH4. So you have 4 atoms. So which means that when you have 4 atoms, you have a proper tetrahedral. But when you have only 2 atoms, the other 2 are the electron pairs, then only 2 atoms are giving the shape. Although the other 2 electrons are also helping. That is how you have the tetrahedral electron geometry. But the shape here is bent. Okay, which means the bond angle is still 109 because the bond angle is coming from AX4, the tetrahedral electronic geometry. So the electronic geometry will tell you how many electron groups you have, so you can determine the bond angle, so you can determine the hybridization. Okay. The number of atoms help you determine the shape of the molecule. So 2 different things here. Okay, so be careful about that. Okay, so then any overlapped hybridizations, okay, will bond with atoms first. Anything that's remaining will be the lone pair of electrons. So like if you have even, so like water, okay, and we're going to do this in a minute also, so I might as well get started on this. Okay, so if you have something like water and you figured out the Ax formula for this, okay, so the Ax formula is AX2E2, which is tetrahedral electronic geometry. If it is tetrahedral electron geometry, what is the hybridization for it, right? So that's what we are talking about. How are we getting there, okay, in there? So let's get there and maybe I'll come back to it eventually. So this is it. Okay, sp, sp2, sp3, sp3, and then the d orbitals are also here. So Lewis structure. So you figure out the number of electron groups in there. Your electronic geometry will help you. Okay, as I said. So if you want, and I have still another slide to show you, which will help you understand this. Okay, also is sp is ax2. sp2 is ax3, sp3 is ax4. Don't worry about these two because those are not part of carbon, but they're still there, okay, just so that you have it in your record. So that is how hybridization is. So if you have an ax2 geometry, what does this mean? Okay, so if you have an ax2 geometry, electronic geometry, 2 electron groups, you have sp hybridization. If you have 3 electron groups, it's sp2. If you have 4 electron groups, it's sp3. Linear, trigonal, planar tetrahedrals, right? Okay, keep it simple. So here is the big table. This is like the best table, okay, of everything, okay, that we have here. So here's the electronic formulas, okay, or groups. 2 electron groups, 3 electron groups, and then in 3 electron groups, you can have AX3 or AX2E. AX2 is just AX2. You can't have AXE. There's not even a shape, okay, going to be for it. So AX2 is the linear shape, right? That's the linear shape. The electronic shape is linear. The shape of the molecule is generally linear as well. Okay, example is BeCl2, which we've already done. The hybridization for this is going to be sp. So the way I've drawn this table is I would like you to follow it this way. Okay, if you can. You can switch these two around if you want to, but leave these two the way it is. Okay, it'll help you. And especially the first 2 columns, okay, 3 columns. So 3, if you have 3 electron groups, then you have the electronic geometry of AX3 or AX2E. The bond angle will be the same for both because it's 3 electron groups. The examples are going to be different, okay, because here you need 3 bonds, you need 3 atoms. In the AX2E, you need 2 atoms and then 1 electron pair. You can see the electronic geometry is the same. Okay, it's the same going to be as the bond angle, right? Hybridization is also the same. Shape is different because shape for sp2 for AX3 is trigonal planar, but for AX2E, because you have 1 lone pair of electron, now it's going to be a bent shape, okay, over here. So there are differences like that you have to really watch out for, okay? This bent shape is not the same as the bent shape coming from tetrahedral because tetrahedrals have a bond angle of 109. This bent has a bond angle of 120, and that's why it's important for you to know the Axe formula and also the hybridization. That will help you. You don't need to have the hybridization for bond angle. You need to know the electronic geometry for bond angle, okay, which is the Axe formula. Once you know the Axe formula, you know the electronic geometry as well, because here you're calculating the number of electron groups, okay, around. I don't want to go every single thing over here, so go through all of these over here, okay, one by one, because again, this is all part of Gen Chem 1. The only new thing we've added here is hybridization, okay, so that's it. So as soon as you have 4 electron groups, all 4 of them will have sp3 hybridization, because sp3 stands for 4 electron group, 1s and 3p. That's 4 electron groups, okay. For all 3 of them, the electronic geometry is tetrahedral, the bond angle is 109, examples are different. Okay, moving on. So here is a problem, okay, for determining hybridization type. Use the hybridization Axe formula to find the hybridization and the shape of N in N2F4. So first of all, here is the structure for it. If it wasn't given, you have to draw the Lewis structure for it. Okay, so now you can see there are 3 bonds and 1 lone pair of electrons on nitrogen. That means it's a 4 group system. AX3E, 3 electrons, 3 bonds and 1 pair of unpaired electron. So once you have a tetrahedral in electron geometry, that's it. It's sp3. You don't have to worry about anything else, okay, in there. The shape is going to be different because it's AX3E. Because of that, it's going to be trigonal pyramidal and not tetrahedral. Tetrahedral is the electronic geometry. The shape is trigonal pyramidal, okay. Again, electronic geometry has to do with the number of electron groups. The shape has to do with how many atoms there are in addition to the number of electrons. Okay, so be careful. All right, so now let's talk a little bit about double bonds and triple bonds, okay, because hybridization should be able to explain multiple bonds as well, okay, because we have double bonds and triple bonds in organic chemistry. So first of all, let's keep it simple. Okay, so let's just talk about something, straightforward. So let's take this molecule, which is carbon dioxide. Carbon dioxide has double bonds. The Axe formula is AX2 for carbon, not for oxygen, for carbon. It's AX2. If it is AX2, then the carbon must be sp hybridized. How am I getting sp? I'm getting sp because s plus p, 1 plus 1 is equal to 2. That 2 is equal to this 2. 2 electron groups, 2 orbitals. That's how I'm getting it, okay? So now let's look at cyanide, hydrogen cyanide, which is this. In case of hydrogen cyanide, we're not talking about hydrogen or nitrogen. It's the central carbon. Again here, carbon is AX2. AX2. Linear hybridization is sp. Okay, again, 2 orbitals, 2 orbitals. That's it. And that's the 2 right here. Determining the hybridization, not a problem, hopefully now. Okay, once you know the Axe formula, you know the hybridization. Now let's talk about how that hybridization works. Okay, so here, this is just an introduction, so I'm not going to talk about this one as much, okay, because we need to understand how the hybridization works. But this tells you that because you have multiple bonds, you can't all have single bonds in there, right? Because if you have single bonds, that's a sigma bond. But because there are multiple bonds, the other bonds, those are actually called pi bonds then, okay? So that's what we have to talk about in case of double bonds and triple bonds. So let's look at ethylene. Ethylene is CH2, double bond CH2. And if you're thinking, why didn't I take carbon dioxide? Because carbon dioxide is a little bit different, okay? Because that's sp hybridized. This one is sp2 hybridized. How do I know this is sp2? I just said it, right? sp2 hybridized because if you look at the central atom, it's going to be AX3, right? A and then 3 atoms attached to it, 3 electron groups. So that's AX3. If it is AX3, the electronic geometry is then trigonal planar, okay, for it. The main reason that we are coming up with sp2 hybridization is because of the 3. When you have something like 3 in there, as soon as you see 3, you know that you need 3 orbitals. You're going to need 1 of the s and 2 of the p, so sp2 hybridization. Okay, so now you know that ethylene or a double bond is sp2 hybridized. Okay. Fine. So now what I'm going to try and explain to you, how does this hybridization work? Okay. So for sp2 hybridization for ethylene, we are again looking at carbon as the central atom, because if you look at the structure, carbon and carbons are the central atoms. So here, central atom, again, the ground configuration is the same, 2s2, 2p2, again, excited state. One electron jumps from here and goes to the p orbital, which is right here. So here you have the excited state. Now, if you look at the red box includes only the 3 electrons, because we need only sp2. So which means we're going to mix only these 3 electrons, which means 1 electron is left over. In the other sp2 that we did, we didn't have any electron in that p orbital, but now we have 1 electron, but we are still going to leave that out. Okay, so here it is left out. And here the new hybridized orbitals, the sp2, are right here. Lower energy, higher energy. Okay, and this is the unhybridized p orbital. This is the hybridized sp2. Now remember, the sp2 hybridized was a different shape. Okay, so the sp2 here shows you it's a little bit more circular. The p, on the other hand, the non-hybridized one or the unhybridized one, is just going to be the normal kind of dumbbell shape, okay, that we have. So now what you're going to have is the one bond that's going to form, okay, which is the hybridized, and that is the sigma bond. So here, if you look at this bond, okay, up here, carbon has a double bond. One of those bonds is this one right here, which is the hybridized orbital. So let me draw it again here for you and show you a little bit differently if this helps. Okay, so you have carbon and then you have carbon and you have the hybridized bonds. So remember, there are 3 hybridized. So 1, 2, and then 3 hybridized bonds. It's not coming out the neatest. I'm sorry about that. Okay, those are the hybridized. Okay, let me try this one again because the middle one is hard to see. Okay, I think I have one extra there. I don't need that. So carbon with 3 of the sp2, right? That's that. Now you also have the unhybridized, and the unhybridized p orbital is just a regular dumbbell, which is this one. Okay. You also have the 4 hydrogens in there. So the 4 hydrogens are going to be bonding right here. So which means what? You have the p that's left over. That p is going to overlap to give you what is called the pi bond. The pi bond is the second bond in there. Now, when you look at a double bond and you're trying to figure out which one is the pi, which one is the sigma, don't worry about it. It doesn't matter. Just one of the bonds is sigma, one of them is pi. That's it. Okay, which one is the pi? It doesn't matter. You don't care. I don't care. All right. What we care about is that you know that there is one pi bond in there. That's it. Okay. Now, every covalent bond is going to be at least one sigma. Okay, there has to be at least one sigma in there. All right, so the rest of them can be pi or not. Okay, so now the bond between carbon and hydrogen, that can only be sigma. That can never be a pi bond. Okay, because hydrogen, first of all, also does not have p orbitals. But even if it did, let's say it was chlorine. Chlorine has p orbitals. Even then, it's not going to be the pi bond. When we say pi bond, that we're indicating it's a double bond. Okay, just by saying it's a pi bond. So that is how this works. All right. So a double bond is going to have a sigma bond and a pi bond. A single bond is always going to be the hybridized bond. Let's look at the triple bond now. Okay, triple bond is the same thing in the sense that now you have triple bonds, so it means you have pi bonds in there. AX2 is the geometry. If AX2 is the geometry, it means you have two electron domains. If you have two electrons domains, that means you have sp hybridization. sp hybridization means that you're only going to mix two of the orbitals, one of s and one of p, so which means two electrons are going to be left over. So two of the p electrons are left over, two are hybridized. It means that, and again let me draw this out for you. So when you have carbon and carbon, so you'll have the two of the sp, so two of the sp. Hydrogen is no problem. You have to have hydrogen there. That's that. This right here, what you formed is the sigma bond. Now what is remaining? What is remaining are the two p orbitals. So you have the p orbital. Remember, you have them going in different directions, right? So one is going x, y, z. One of the p is gone. You don't know which one. It doesn't matter which one. Okay. The other two are going to be right there. So now they are going to overlap, and once they overlap, you're going to get pi bonds. So which means you're going to have two pi bonds now. One is the overlap of the purple, whichever one that is, X, Y, Z, it doesn't matter, and the other one is going to be for the green one here. Okay, so you have a sigma bond, and you have a pi bond, and you have another pi bond. Okay, so one sigma bond and two pi bonds in a triple bond. The hybridization that is happening here, okay, is dependent on the electron groups. That is how you determine the hybridization, all right? And how are you determining the electron groups? You're determining the electron groups from the Ax formula, all right? So there's, a very systematic way of doing it, and if you do it that way, you will not go wrong, okay? Because it's very systematic, and provided you remember how to do all of these hybridizations, you'll be fine. Now, in general, I will say to you that this diagram that I have in the middle, you're never asked of that. Okay, you are never asked to draw this electronic diagram. You need to understand this to know hybridization, but honestly, the most important thing is on the top and the bottom. Okay, in all the slides that we have gone through. Okay, those are the important things, the top and the bottom. The middle part is just for you to understand how hybridization occurs. Okay, but otherwise, the Ax formulas are important, the angles, the shape, those are important things here. So here is one on predicting hybridization, and here's the Lewis structure. So on nitrate, of course, you have to first draw out the Lewis structure, and this is the Lewis structure for it. And if it is correct, which yes, it is, then you have the formula for AX3. If it is AX3, then the hybridization is sp2. How sp2? 1s and 3p, and that is AX3. Okay, so keeping it simple, all right, don't make it more complicated than that. All right, so let's look at all the properties together for ethane, ethene, ethyne, which essentially is a single bond carbon-carbon with a double bond carbon-carbon and triple bonds. Okay, so which is the sp3, sp2, and sp hybridization. So for sp3 hybridization, the shape is going to be tetrahedral. For sp2, trigonal planar. sp is linear. If you want to add for yourself, and I haven't done it because I've done it so many times before, is the Ax formulas. Okay, so this is AX3, AX4, AX3, AX2. Okay, if you want to write that down. Okay, so the bonds that you have in these kind of organic compounds is that you have all sigma bonds for sp3, which is this. Okay, right here, that's the sigma bond. For sp2, it's going to be 1 sigma, 1 pi. And for the triple bond, it's going to be 1 sigma and 2 pi bonds. Okay, that's how the bonding is in organic compounds in general. Now, the examples I gave you before have single bonds for sp2 and sp, but those were inorganic examples, okay? Those were BH3, BEH2, and you can find several examples like that also, okay? So, but in organic compounds, generally this is going to be the trend. The bond angles have not changed also, because for sp3, which is tetrahedral, is 109, sp2 trigonal planar is 120, and so on, okay? That has not changed. The bond length has changed, okay? And you can see that the bond length is getting shorter. The more bonds you have, the shorter the bond, okay? Because they're getting closer. Why are they getting shorter? Is because there is more overlap of orbitals, okay? So in the case of sp, you have 3 orbitals that are overlapping, so they get closer together, okay? So that's the bond length for you. Again, don't remember the numbers, remember the trend, okay? That's more important. The bond energy is much higher for sp, which means that there is more energy in sp. Why is there more energy? Is because there are more pi bonds, okay, in there, and pi bonds generally have higher energy, so this will give out more energy, which means what? It means that sp are more reactive also, okay? The sp3 not so reactive. And then finally, here are some organic examples. And again, this may not be the most important column for you right now, or row for you right now, because we don't know any of these kind of molecules, but it's just given there for future in case whenever we need it. Okay. So here is an example for pi bonds and sigma bonds. Is how many pi bonds and sigma bonds are in each of the following molecules, and what is the hybridization. Okay, so for the first one here, you can see it's sp 3, and so for sp3 this is going to be let's see, what is it, sp3, yeah, of course sp3, and then the bond angle here would be 109. Are we asked the bond angle? We are not asked for the bond angle, just how many pi bonds and sigma bonds. So this has 4 sigma bonds, okay? In here you can always pause me and do this yourself, and then look at the answers if you want. This is sp2 because I see a double bond. I see a double bond, so sp2. And so here, 5 sigma bonds and 1 pi bond. Okay, so here you have the 1 pi bond, but 1, 2, 3, 4, 5 sigma bonds, okay, in here. So in the last one, you can see that there's going to be plenty of pi bonds. So there's 1 pi bond here, 2 pi bonds here, and the rest, everything is going to be sigma bonds. And the hybridization, again, for a double bond is going to be sp2. Triple bond is sp, and any kind of a tetrahedral would be then sp3, right? So sp3, sp2, there we go. You have 10 sigma bonds and 3 pi bonds in total, okay? So that's that. Okay, the last theory we need to talk about is molecular orbital theory. And molecular orbital theory is a little bit different in the sense that it explains even more than the valence bond theory. It goes deeper and deeper into the atomic orbitals. Not only that you have the atomic orbitals, but what are the energy levels also, okay? So we go into deeper overlaps in here. We go into wave functions that you might remember. Wave functions were the psi positive, psi negative, okay, that we talk about. So you can have 2 different kinds of orbitals. So here you have atomic orbitals and molecular orbitals. Atomic orbitals are occurring, of course, in atoms. When they combine, when they overlap, you form a molecular orbital. When you combine them, what is overlapping? Is it the psi positive? Is it the psi negative? That is what makes a molecular orbital bonding or anti-bonding. So if you have the same kind of, and it's not a charge, okay, psi positive is not a charge, it's actually just the sign. If you have psi positive overlapping with psi positive, that is called bonding. If it is the opposite, then it's called anti-bonding. Okay, so there are 2 kinds of molecular orbitals as well. Anti-bonding, because they have the opposite charges, are going to be higher in energy. Okay, if you want to read more, you can read over here. I've explained very small over here. Okay, you can see that I'm almost done with my PowerPoint here. So I haven't explained a whole lot because I'll cover it later on also, okay, in there. So the only example I've given here is that for hydrogen, so you understand the concept. So hydrogen has only one electron and only one orbital. Okay, so one s1, that is it. So one electron here, one electron here. So it has an atomic orbital. When those two atomic orbitals combine, you form two molecular orbitals. Those two molecular orbitals, one is antibonding and one is bonding. The bonding MO is lower in energy, the antibonding is higher in energy. The bonding MO is the one that's going to have the electrons, because electrons, just like people, like to have low energy. Okay, so they like to be more stable. All right, so the lower energy orbital, which is the bonding MO, is going to have all the electrons as much as possible. Okay, now this is a very simple molecular orbital diagram because you only have the one sigma bond, right? That's it. But if you have, as we were counting before, 10 sigma bonds and 3 pi bonds, you'll have many, many, many more of these. Okay, and then you have to place them in the energy diagram. So it can get a little complicated. So you really have to be good in knowing your orbitals, okay, in those. So right now we're not going to focus too much on it. We're going to finish right here. So just you understand these terms, okay? Later we'll come back to it. And that's it, okay, for this PowerPoint. I know it's been long, but hopefully you got hybridization, because that's the main thing from this PowerPoint is hybridization.